Good morning, everyone. So today is circular dynamics lecture number 2, and let's have a quick recap of what we had done in the previous class. So in the previous class, I think we were discussing the different. Basically, we were trying to discuss a new term which is known as centripetal acceleration. Centripetal acceleration is the acceleration which is directed towards the center of the circle. Now we saw centripetal acceleration, we saw tangential acceleration, and we also saw their functions. We saw that tangential acceleration is either in the direction of velocity or it is in the opposite direction of velocity. It always increases or decreases speed. So speed increase or decrease or changing the magnitude of velocity is the job for tangential acceleration, whereas centripetal acceleration or normal acceleration or radial acceleration, let me tell you why it has got different names. It is known as normal acceleration, AN, normal, because this one is tangential. So if I look at the circle, if I say tangential acceleration is just like here, it is tangent. So I draw it by the red line. This is tangent. Then the other acceleration will be normal. When do I say normal? I mean that this acceleration will be like this. So therefore, it is known as normal acceleration. I can also call it perpendicular acceleration. It is known as radial acceleration, AR, because it is along the radius or it is radially inward. So along the radius of the circle, and therefore it is known as radial acceleration. It is also known as centripetal acceleration because it is towards the center. Centripetal means seeking center, towards center. And that is why it has got four names: A perpendicular, A normal, A radial, or A centripetal. Then we also saw a brief introduction of the total acceleration. The total acceleration is a vector, and this A vector includes tangential acceleration as well as centripetal acceleration. And this A vector is the mother acceleration. This mother acceleration can be broken into two daughters. One daughter, A tangential, will change the speed of the particle, the magnitude of velocity. The other daughter, the centripetal acceleration, will change the direction of velocity of the particle. Up till here, anyone has any doubts? Please raise your hand so that I can clear them right now, right away. Else, I will move on to the next part. So I'll give you a minute to let me know of any doubts that you might have. Else, I will move on to the next part. 1 minute is what you get. I hope everyone has gone through this, everyone has seen this, and we all remember this. This was no doubt, so I'll move on. Now, the next heading would be relation between, and today's class will be dedicated to this, relation between linear and circular quantities. So here what we are going to do is try to understand the relation between linear and circular quantities. Now, what do I mean by linear quantities? Linear quantities are quantities that we have been using till now, namely displacement, velocity, acceleration. These were the quantities that we studied in chapter number 1. You can call them linear quantities. Now we have come across these circular quantities: angular displacement, angular position, angular velocity, angular acceleration. So now what we are going to do is find out the relation between these linear quantities and these circular quantities. So what is the first thing that we'll do here? Relation between L and theta. Now what do you mean by L and theta? L will refer to the linear distance, how much distance the body has moved, and theta relates to how much angle it has turned. You can also call it delta theta. You can also call L as delta L. Doesn't matter. I'm just not wanting to use this delta term, and that is why I'm just using L and theta. Now what I'm going to do is, oops, this is no good. Okay. Oh, can't change the shape or what? Okay, I can make it circular. It looks okay. So this is a circle. Now suppose a body is moving in this circular path. Basically, we are now concentrating on circular motion. So body is moving on a circular path. Now, let us suppose that at some point in time, the body is at point A. At some other point, the body is at point B. So what I have done is I have joined A to O and O again to B. A is the initial position of the particle and B, let us say, is the final position of the particle. Now let us say that this body has turned, or the angular displacement of this body is delta theta. Let me call it delta so that it does not confuse you. Let me call it delta theta here, and let me call this as del L, where L will stand for the distance, not displacement. Okay, so it has turned by an angle of delta theta. So the displacement, angular displacement, which is a scalar quantity, angular displacement is delta theta from A to B. Now, it has turned an angle of delta theta, and let us say that the radius of this gentleman, I mean the radius of this circle, is R. Whenever we are on a circular, we are doing a questions on circular motion, we will have to deal with this R, radius of the circle. I hope you are aware of it. So the radius of the circle is R. It has turned by an angle of delta theta, or the angular displacement is delta theta. Now, if someone asks you how much distance this body has moved, obviously it has changed its position. Whenever something moves, it has moved a distance, it has traveled a distance. That is never negative, we all know that. Now, if I ask you how much distance, or delta L, what is the delta L, or the distance this body has traveled, can you give me the answer for that? How much distance this body has moved? If I talk about the linear distance this body has traveled, it has moved by an angle of delta theta. Remember, this delta theta has to be in radians. We are talking about SI units, so this delta theta is in radians. Now, can anyone tell me how much distance this body has moved? Anyone? Now, if I talk about that distance, it would be good to mark it on the diagram itself, and that is why I have rubbed that radians. So what I'll do is I'll write this radians here on this side. Now what I want you to answer is how much distance this body has moved. Now to understand this distance would be equal to the length of this path. How much is the length of this path? That is the distance this body has moved. When it has turned by an angle of delta theta, this much is the distance delta L that this body has moved. Can you now tell me the relation between delta theta and delta L? What would be the relation between delta theta and delta L? I'm waiting for your answers. Anyone can give me an answer by common sense or common knowledge. What is the answer for this delta L, which is the distance the body has moved, or it is the length of the path AB the length of the path AB, length of the path AB. Remember, delta theta is in radians. Delta L will be in meters because R, the radius, is in meters. Can anyone tell me that? No one? Santosh is giving me the answer. Right, Santosh, this is correct. Santosh has given me the answer. Delta L will be equal to R times delta theta. This is exactly correct, or I can also write it like this. Delta L is equal to delta theta multiplied by R. Now, how do I get to this equation? How do I get to this equation? Everyone must know this. If you don't know this, don't worry. The relation comes from the simple fact that this delta theta, or the angle in radians, the definition of angle in radians is the length of the arc, which is delta L divided by R. So we have derived this relation from the definition of radians. The angle that the body has turned in radians, delta theta, is nothing but the length of the arc divided by the radius of the arc. Do you all understand this? Can I have some raised hand that we understand this, sir? Only 14 people have understood this. That is not good. Rakesh, Yashwant, Venkatesh, Vasant, Tarun, Gaur, Sidhu, Harshita, Satya, Satvika, Sarda, Sai Sarda, Padmakant, where are you? Niharika, sleeping. Karthik, Shashank, Kevin, Jyotsna, Jayashankar, Jagdish, Ajay, Akshaya, Abhiram, dot. Who is this dot? Everyone has a name, and it's always better to use your name rather than using dot and cross. We will be using this dot and cross just now. Just give me a minute. So this is the relation between delta R and delta theta. No, delta L and delta theta. Delta L standing for the distance, length of the path. Delta R, delta theta standing for the angular displacement. Relation between linear and circular, or linear and angular quantities. This is the first relation. I'll give you a minute to note this down, and then we will move further. If you have any doubts, you can raise it in the meantime. Well, I hope all of you have noted this down. Let us move on to the next thing. We have related distance, linear distance traveled with angular displacement. What is the next thing that we must relate now? What should be the next thing that we must relate? Anyone? Can anyone look into the future and tell me, sir, this is the next thing that we must relate to? Who is going to tell me that? See, this class gives you a chance to look into the future, to move into the future. Einstein says that you can do it. If you move closer to the speed of light, travel around 1 over 2 years or 4 years and come back, you will have moved into the future. The faster you go, the speed of the light remains same, but the time gets slower. So what is the next thing? Reddy, yes, Reddy, try to send message on the other ID, because on this ID it's difficult to see your messages. The next thing that we must relate is V and omega. Linear velocity as we know, and omega, which is the angular component, angular part. Let us now see how we can relate this. And I'm not going to get into some fancy derivation. We'll just look at how they're related. It's as simple as that. O is the origin, right? And obviously I have R. Oops, what I'm doing here. Don't understand what I've done. R as the radius of the circle. These are the two things that are already known. Now let us say that this particle is here at point A. Now let us assume that it is rotating. It is moving in a circular path, and this is how it is rotating. It is rotating with an angular velocity omega. Now when I write this velocity like this, angular velocity like this, it is rotating like this. So the axis is coming outward. This outward axis is actually your plus z axis, and therefore this omega is positive. It is along positive z axis. But I can't do all those things. Let us forget about all those things. I just can't keep on naming and renaming my ID. If you can't send messages on that ID, forget about it. Okay, you must understand that ID I'm taking the class. If you can send message on that ID, do it. I'll do it on the other ID. It takes a lot of time for me to do all this naming and renaming, and I'm not good at that. I'm not concerned. Okay, so this omega is like this along positive z axis. Omega is like this. Now, if omega is like this, the velocity that this particle will have at this point, and if I should mark them correctly, is like this. This velocity at this point will be like this. If I move on to point number B, we have already drawn this diagram. This velocity would be like this. The magnitude has remained same, but the direction has changed. If I move on to the third point, point C, the velocity goes downwards like this. If I move on to the fourth point, point D, velocity remains like this. I've assumed that omega remains constant, so the magnitude of velocity will remain constant, and you will just see it in a moment why this remains. Now, looking at this velocity, since this is moving in a circular path, this velocity is always along the tangent. This velocity is always along the tangent. In fact, wherever a particle is moving, whether it is moving on a straight road or is moving on a curved path, every curve is a part of a circle. Remember this. Every curve is a part of a circle. Even a straight line is a part of a circle. The only relation, only difference is when you have a straight line, if something is moving on a straight line, the radius of that circle, we call it radius of curvature. We call it radius of curvature. The radius of curvature of a straight line is infinite. Every curve is a part of a circle. So whenever a particle is moving on whatever path, whether it's a circular path, whether it's a straight line path, whether it is zigzag path, is always moving at some point around a circle. That circle has a center. That center is known as center of curvature, and that radius is known as radius of curvature. Here, as you can see, in this particular case, it's a very simple question. It's a very simple scenario that the particle is definitely moving on a circular path. Now, this velocity is always along the tangent, and hence we can call it Vt, 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 Vt. So from now onwards, we are going to call velocity as Vt, V tangential, because it is always along the tangent of the circle. You will see, sir, not every time the particle is moving on a circle. Yes. However, howsoever the particle is moving, at every particular point, it is moving around a circle. That circle has a center, center of curvature. That circle has a radius, radius of curvature. So you can always call this velocity as Vt, tangential velocity. Do we understand this? Can I have some raised hand that you understand this, sir? Only 11 people have understood this. Not good. What about the others? Rakesh, Yashwant, Vijay, Venkatesh, Vasant, Tarun, Varshita, Suren, Sidhu, Satya, Satvika, Sai, Padmakant, Krishna, Kartik, Shashank, Kevin, Josana, Jaya, Jagdish, Deepak, Charita, Akshay, and Ajay. We are all there? Okay. Vt and omega. Now, the actual relation between these two quantities is this one. And this is the actual relation. The actual relation, the vector relation between Vt, tangential vector of velocity, is this omega cross r. It is the cross product of omega with the radius vector. And how is this radius vector directed? This radius vector is directed, if I draw this radius vector and I will draw it with this blacking, this radius vector is directed like this. This is my r vector. At this point, r vector is here. At this point, r vector is here. At this point, r vector is here. I hope everyone understands the direction of r vector. At this point, this r vector is like this. Now, it is the cross product of two vectors. If you know the direction of cross product, it is given by the right hand thumb rule. So the first vector will be omega. If it is like this, and r vector is like this, you can see the velocity will be upwards. This is how you can find out the direction of velocity. You don't have to do cross product here just now. If you see something moving like this, velocity will be here like this. If something is moving in the ulta sense, clockwise sense, the direction of velocity will just reverse. Do we all understand this? Can I have some reason that we understand this? If something is rotating like this, velocity will be like this. It is very easy to understand. This is no physics, this is just common sense. Now this is the vector relation. Now when you have vector product, you have omega into r into sine theta. So I can write it simply like this. If I talk in terms of magnitudes, Vt, which is the magnitude of velocity, tangential velocity, will be omega multiplied by r. Here I am not talking about the vectors. Here I am only talking about the magnitudes of tangential velocity and omega, the angular velocity. Omega, the angular velocity, and Vt, which is the tangential velocity. Are we getting this relation, everyone? The equation number 1 is the vector relation that gives me both the magnitude and the direction of Vt. The second equation is the scalar equation, which only gives me the relation between the magnitudes of Vt. Now this magnitude of Vt, tangential velocity, becomes your speed. You can call it tangential speed, no problems. Speed is the magnitude of velocity. Instantaneous speed is the magnitude of instantaneous velocity. So tangential speed, which is instantaneous tangential speed, is the magnitude of instantaneous tangential velocity. Do we all understand this? Can I have some reason that we understand this? Okay, now look at this very important point. If omega is constant, it does not change in magnitude, it does not change in direction. This will imply that Vt is constant. Now remember, when I talk about Vt, I am not talking about Vt vector. I am only talking about the speed. Tangential speed is constant. Everyone understands this? The tangential speed is constant. Tangential speed is constant, not tangential velocity, because as you can see, tangential velocity is definitely changing its direction. At all points, it is changing its direction, but it is never changing its magnitude. And here we are only talking about the magnitude of tangential velocity. Now, this type of motion, when omega is constant and tangential speed remains constant, this type of motion, when omega is constant, tangential speed is constant. What is the name of this motion? What do we call this motion? We all have studied this motion. What do we call this motion if omega is constant and tangential speed is constant? What do we call this motion? Anyone can give me an answer for that? Uniform. What uniform, Yashwant? Uniform. What uniform? Uniform circular motion, or simply UCM. That is correct, Niharika. Uniform circular motion, or UCM. This is how you relate Kartik with the things that you studied in the first chapter and the things that we are studying right now. Do we all understand this? Can I have some reason that we understand this? Now I'll wait for a minute. In that minute, you would be getting time to note it down and ask if you have any doubts. I hope everyone has noted this down. Let us move on to the third relation. What could be your third relation? What will be the third relation that is going to relate? Relate what and what? Niharika says A and alpha. Niharika, you are partly correct and partly not correct. How am I going to relate? Obviously, I am going to relate accelerations here. I have related distance, angular displacement and distance. I have related angular velocity and tangential velocity. That is why I use the term tangential. That is why I use the term tangential. Karthik is saying A and AC. No, Karthik, not A and AC. I use the term tangential velocity and omega in the second case. There was a reason I did that. There was a reason I called velocity as tangential velocity. There was no reason for me to tell you that. But whatever I do it for a purpose. We discuss about the relation between AT and alpha. That is correct, Niharika. AT, tangential acceleration and alpha. These are the two things that are related to each other. Very correct. AT and alpha. Both are vectors and they are related to each other. That is absolutely correct. Well done, Niharika. How are they related? Exactly the same way. Oops. Exactly the same way as VT and omega are related. I'll give you a chance to tell me how AT and alpha are related. Let us say this particle is at point A. And let us assume that this alpha is like this. Again, it is an actual vector. So now alpha is like this. Now, can anyone tell me? Forget about velocity. How is the velocity? How is the particle moving? That is not our concern because we have already seen Vt and omega relation. Right now, I am concerned with tangential acceleration and alpha, and the baton passes on to you. Can you tell me the relation between At and alpha? And how will At look like when alpha is like this? Time starts now. Let's see who gives me the answer. Mark this by green color. How would At look like? What will be the relation between At and alpha? It's very simple. 2 plus 2 makes 4. It is as simple as that. No one knows? That is sad. Still no one? I hope I am audible and visible to all of you. Relation between At and alpha. How would At look like when alpha is here? Well, no answer, so I'll have to do my job. No, bird is not on the pause, sir. I can see it on the thing. Bird is not on the pause. So it is like this. Tangential acceleration will be going like this. It is exactly similar to the relation between omega and v. And now I can write this relation. At tangential acceleration will be equal to alpha cross r. It is exactly similar to the relation that we had seen equation number 1, which is the vector equation between At and alpha. It looks like this. Equation number 2, I can write the magnitudes. At will be equal to alpha multiplied by r. This is the vector. First is the vector equation. Second is the scalar equation. If alpha is 0, At the magnitude becomes 0. If AT is 0, that implies omega and Vt is constant. And what do you call that motion when omega and Vt is constant? We all know this. What is that motion known as? That motion is known as, yes, Niharika, this is known as UCM. See how beautifully everything is relating to each other. Alpha, AT, omega, Vt, how they relate to each other. Very smart, very sweet relation that will make us understand how good is physics. Conceptual. Now, I can write another thing. If alpha is constant, and I'm talking about the magnitude here. If alpha is constant, AT, which is the magnitude of tangential acceleration, is constant. As you can see here, at point A, AT is like this. If I go to point B, AT will remain same in magnitude, but it would have definitely changed its direction. I'm not talking about the direction here. I'm talking about the magnitudes. At point C, if I go, no prizes for guessing this. AT will be downwards. Magnitude remains same. Direction changes. At point D, again the magnitude remaining same, but the direction is changing. I'll give you a minute to note this down. Note this down, then we will talk something else about AT as well. A minute to well, I hope you have noted this down, right? Now, remember one thing over here, that if alpha is 0, there is no tangential acceleration. The magnitude of velocity, the magnitude of tangential velocity remains constant, and this becomes a uniform circular motion. If alpha is not there, it is UCM. That means if alpha is there, omega will change, definitely. Vt will change. Vt is always changing in direction. Vt is always changing in direction. Who is changing that Vt in direction? Centripetal acceleration. That is the next thing that will come. Vt is always changing in direction, but Vt only changes in magnitude when alpha changes. When there is alpha. Or wherever there is tangential acceleration comes because of alpha. Wherever there is tangential acceleration, your velocity changes in magnitude. Tangential acceleration changes magnitude of velocity. Tangential acceleration changes magnitude of velocity. Tangential acceleration changes magnitude of velocity. We all understand this. Can I have some reason that we understand this? Yes, sir, we understand this. Tangential acceleration changes the magnitude of velocity, and now comes the killer punch. And this is the killer punch. What is tangential acceleration? Tangential acceleration, and you will note this down from the sheet. The component of acceleration directed along the tangent of the circle is called tangential acceleration, which is known. We know this. It is responsible for changing the speed of the particle. So I can write AT as dv by dt. Remember, I am not using the vector sign here. I am using the scalar sign. That means AT becomes the magnitude of tangential velocity, and Vt, I should write it as Vt. Vt becomes the magnitude of tangential velocity, which is speed, tangential speed. So I can write it like this. It is rate of change of speed. Wow. Rate of change of speed, new term, but now it makes sense. Rate of change of velocity. Who is changing velocity? Acceleration. Who is changing speed only? Speed only. Speed only. Speed only. It is the daughter coming from the mother. Tangential acceleration changes your speed. AT becomes alpha into R. Do we understand this? Can I have some raise hand? A very important point that you must understand here. Tangential acceleration changes speed. I'll give you a minute to note this down. I hope everyone has noted this down. Tangential acceleration changes speed, which is the magnitude of velocity, and hence it is known as rate of change of speed. Very important thing that you must remember. And then there are three important points that are coming to you right away. Point number one, in vector form, AT vector is alpha cross R. We have already seen this. Number two, if tangential acceleration is directed in the direction of velocity, if AT and VT are parallel, then the speed of the particle increases. Point number three, if tangential acceleration is directed opposite to velocity, then the speed of the particle decreases. 1 minute. I hope it is very, very clear to all of you what you have to note down. 1 minute and I would be back. Well, I hope everyone has noted this down. The next thing is centripetal acceleration. Relation between centripetal acceleration, and Vt and omega. How are these things related? Now let us first write what is centripetal acceleration. Tangential acceleration changes the speed, which is the magnitude of velocity. Centripetal acceleration is changing the direction of velocity. We all know this. There is always a centripetal acceleration because the direction of the velocity is always changing. Direction of velocity is always changing. Therefore, there will be always centripetal acceleration. Whether it is UCM, whether it is not UCM, centripetal acceleration is always there. Centripetal acceleration is always variable because it always changes its direction. Even if the magnitude is constant for centripetal acceleration, it is towards the center. It is always towards the center. If I draw a circle over here, and the particle is moving like this, here it is like this, here it is like this, and here it is like this. Now the centripetal acceleration, which I am going to draw in red, will be towards the center. So here centripetal acceleration will be like this. At this point, centripetal acceleration is like this. At this point, the centripetal acceleration is like this. At this point, the centripetal acceleration is like this. Is always towards the center. So even if the magnitude is constant, the direction is always changing. It is also known as radial acceleration or normal acceleration. I've already told you why it is radial or normal. Then last thing is, what is the vector relation? Vector relation is coming up your way. A centripetal is equal to omega cross Vt. This is the vector relation. Omega and Vt ka cross product. This is the cross product of omega and Vt. Will not go much into that. Why it is like this? It is just like this. It is the cross product of omega with Vt. If I want to write it in the scalar form, AC can be written as omega multiplied by Vt. This is one way of writing it. The other way of writing it is, you can write Vt as omega into R. So this becomes omega squared into R. The other way of writing this is, you can write omega as Vt by R. So you can write it as V square T by R. Am I clear with this 3-4 formulae that I have given for centripetal acceleration? The vector formula is omega cross V. The scalar formula is omega into V, or omega squared R, or Vt squared by R. It is always added towards the center, hence it is known as centripetal acceleration. It is always variable because it is always changing its direction. So if you can see, if omega is constant, I will write it here. if omega is constant, AT is constant, AC is constant. But when I say AC, I am only talking about the magnitude of AC. The direction of AC is always going to change. As you can see, AC, the magnitude will remain constant if omega is constant, because it is omega square r. The magnitude will remain constant, but the direction will keep on changing. If you have understood this, please raise your hand so that I know that whatever I'm telling you is making sense. Yes or no? I want raise hands from each and everyone in this same, because if you understand this, you have understood the entire topic. If you have not understood this, something is missing somewhere which you have to find out. Let us pick people up and ask. Rakesh, Venkatesh, Varsha, Tarun, Narshita, Sunil, Sidhu, Satvika, Sana, Sai, Pranay, Padmakant, Krishnakant, Krishna, Shashank, Kevin, Jyotsana, Janu, Jagdish, Tejasvi, Deepak, Charita. Everyone is there in the class. I'll give you a minute. I'll end this class here, in fact, because I already see that the time is over. So we will end this class here on centripetal acceleration. In the next class, we'll be just winding it up with total acceleration. I've already told you what total acceleration is. Total acceleration is rate of change of velocity. Tangential acceleration was rate of change of speed. This is rate of change of velocity, and it is simply equal to AR vector plus AT vector. If I'll give you a small homework here, This sheet is already there with you. You already know what is total acceleration. I will give you homework to note this down from here to here and this diagram. This is tangential acceleration. This is radial or centripetal acceleration. This is total acceleration. It makes an angle theta with the radial acceleration. How do you find out the direction? Well, do it and let me know how it is done. The direction is given ulta. Remember, the direction is always given. Here it is wrong. The direction is always given from the tangential acceleration. So just make a correction that instead of theta here, just put the theta there. The direction is always with the tangential part. So the direction with the tangential acceleration is AR by AT. This is simple vector notations. If you can note this down in the next class, before coming to the next class, we will save a lot of time, and time is very important. So if you can note this down, will you be able to do this? Can I have some raise hand that we will be noting this down before coming to the next class? What is total acceleration? Everyone will do that. So on that note, I'll wind up today's class. I hope you have enjoyed this, what we have done in today's class. Well done, Karthik. Well done. You are very quick that you have already noted this down. Very well done. I'm very impressed with your spirits. We'll meet in the next class. We'll just wind it up and we'll solve one or two problems and quickly move ahead. And once we have done this, we'll move on to what is centripetal force. Just multiply this centripetal acceleration by mass and you will get centripetal force, and we would have done your circular dynamics, and we'll quickly move on to your work per energy chapter. I hope you have enjoyed this class as much as I've enjoyed in giving this lecture. If you miss something, you can always see the recorded part of this lecture. It's always available. See you in the next class. Stay at home, stay safe, get vaccinated, take care. I'll meet you in the next class. Bye bye. I'm here if for any doubts, please raise them.